So in section 10.1, we're going to talk about goodness fit. So in this section, we have a probability experiment, and we're going to have a fixed number of independent trials. And for each of the trials, there's going to be more than two possible outcomes. So what we're going to do is we are going to classify those outcomes as categories, okay? So we're going to be using something called the chi-square goodness of fit test. And what this test does, it's going to determine whether or not the frequency distribution fits our expected frequency distribution. So in this case, our null hypothesis is always going to state that the frequency distribution fits the specified distribution. So that's like what they're claiming. And then the alternative is going to be that they don't fit that specified distribution. So let me show you what I mean by an example of this. So each of our outcomes for tax prep methods is classified into our categories. So our categories in this case are accountant by hand, computer, family friend, or a tax preparation service. So the percentages here are the probability for each of our outcomes, okay? So in this case, our null hypothesis would be that the distribution of tax preparation methods is 25% by accountant, 20% by hand, 35% by computer software, 5% by family or friend, 15% by tax prep service, okay? And then the alternative would be it doesn't fit into that claim or expected distribution, all right? So what we're going to do is we are going to calculate our test statistic by using the observed frequency, and that's represented by O, and then our expected frequency. And our expected frequency is represented by E, okay? So the expected frequency would be what you are thought to get. So like, for instance, if I have a, I don't know, bag of Sour Patch Kids, and what they come with, like yellow and red and green and blue, I think, is it 4 colors? And so then let's say I have a bag that has 100 Sour Patch Kids in it. I could say that I expect it to be an even distribution. So I would expect 25%, 25 of the candies to be yellow, 25 to be red, 25 to be blue, 25 to be green. And then I would, actually get a bag and I would open it up and then I would count. And so that would be my observed frequency when I counted, and my expected frequency would be me doing the math and dividing 100 by my 4 colors. Okay. So, boop. What we're going to do now is we are going to actually find our expected frequency. So we've got 300 adults. And so 300 adults, what we're going to do is we're going to take our percent and we're going to multiply that by 300. So for the first one, I'm going to say 0.25 times 300. Okay, and I'm going to get 75. So let's go ahead and do that for all of them. 0.2 times 300, and we'll get 60. 0.35 times 300, and we'll get 105. 0.05 times 300, and we're going to get 15. And last but not least, 0.15 times 300. 45. Okay, so now that we have that, a couple of other things I want you to keep in mind is in order for this to work, we have to have the observed frequency obtained by using a random sample. And each of the expected frequencies has to be greater than or equal to 5, okay? So those are the two keys that we need in order for this test to be valid. So what we're gonna do is, the first thing that I want you to notice is we have K minus 1, K standing for our categories for our degrees of freedom. And here is our formula for our test statistics. So what we're essentially going to be doing is we are going to be subtracting our observed minus our expected value, squaring that, dividing it by the expected value, and then we're going to add all of those pieces together from each of the different categories. The other thing that we are keeping in mind is that this is always going to be a right-tailed test. So what does that mean that it's a right-tailed test? That means it looks like this. So we're going to get some value, and this is our rejection region here. Okay, so here is a list of our steps. So first, you want to make sure that your observed frequencies are at least 5. State your null, state your alternative, identify your level of significance, determine your degrees of freedom, and then you can find your critical value from the table in the back of the book. It's table 6, appendix B. Determine your rejection region, and remember, right-tailed test. And then you're going to use the formula to find your test statistic, okay? From there, you can make a decision to reject or fail to reject, and then you're going to interpret that decision in the context of your claim, okay? So we've been getting really good at this. So let's go ahead and knock this one out, okay? So we're going to go through this entire example. So our null hypothesis, which is in this case our claim, is accountants were 25% by hand, which I don't know why you would do that for your taxes. That's too much work. Computer software, 35%. Family friend, 5%. And tax prep service, 15%. Okay, so then my alternative hypothesis is going to be that it doesn't follow this distribution. Okay. All right, so we're going to use our formula now. And actually, before we do that, let's find our critical value. So our degrees of freedom, remember, is categories subtract 1. So in this case, I've got 1, 2, 3, 4, 5 categories. So 5 subtract 1 is 4. Okay. And if I look in the back of the book using my 1% alpha significance level, I am going to get my critical value as 13.227. So what is that telling me? That's telling me that anything greater than 13.227 is in my rejection region. Okay, so now let's go ahead and use the formula. Okay, so remember the formula is sum of your observed subtract your expected value squared, all divided by your expected value. Okay. So what you're going to do is you're going to take each of the categories and subtract the observed minus the expected. So in the first case, I'm going to have 71 minus 75 squared divided by 75. And then for the by hand category, it's going to be 40 minus 60 squared divided by 60. And then we're going to have 101 minus 105 squared divided by 105. Come on, Ben. Oops, 35. All right, so if I put all of that into my calculator, I'm going to get about 35.121. So the question is that in the rejection region? And the answer is yes. So we are going to reject our null. And what does this mean? It means the distribution is different. Okay, let's do another one. Okay, so for this one, it's telling us that a researcher is claiming that the different colored candies in a bag of dark chocolate M&Ms is uniformly distributed. Okay, so what does uniformly distributed means? It means that all of the colors are going to occur equally. All right, so we've got 500 dark chocolate M&Ms. Do they make dark chocolate M&Ms? I don't even know. Okay, so how many total different colors do I have? 1, 2, 3, 4, 5, 6. So I'm going to say 500 divided by 6, and that's going to give me 83.33 repeating. All right, so I'm just going to go to 83.33, which tells me my expected value for each of these colors is 83.33 because I am expecting them all to be the same. All right, so in this case, my null is that the distribution is uniform. And then my alternative would be it's not uniform. Okay, so the next thing that we need to do is we need to figure out what our critical value is. So in this case, our degrees of freedom is we've got 6 different colors, so 6 minus 1, which is 5. And at an alpha level of 10%, our critical value is 9.236. And where am I getting that? I'm getting that from the back of the book. So that's telling me that anything greater than 9.236 is in the rejection region. Okay, so now we're going to do exactly like we did for the last problem, where we're going to subtract each of our observed frequencies minus our expected. So 80 minus 83.33 squared over 83.33 plus 95 minus 83. Plus Oop, 83. Oop. It's 83 minus 83.33. Here we go. Now I got it right. Coffee hasn't kicked in yet. All right, plus what, 76? Oops. All right, last one. Was it 78? All right, so if I do that, I'm gonna get about 3.106. So my question is that in the rejection region? And it's not because it's somewhere over here. 3.106. Okay, so that means we're gonna fail to reject. Okay, so what does that mean? It means the distribution is pretty much uniform.